Hello, good morning and welcome to biology class. My name is Hanson and today we'll be doing something on what I call biological molecules. What are these molecules? Why are they known to be biological? Okay, now the molecule is made up of two or more elements. So when we have these two or more elements in biological systems, in living things, then we refer to them as biological molecules. In other words, we can say that a biological molecule is the smallest unit of chemical substance in a living organism. A biological molecule is the smallest unit of a chemical substance in living organisms. So, these chemical substances are made up of elements, irregular elements that you know, like carbon, nitrogen, oxygen, sulphur. They all come together in different combinations to give us different forms of biological molecules. Now, when several of these molecules come together, they can form what we call a macromolecule. A macromolecule is more like a larger molecule. A molecule having several units of smaller molecules, several units of smaller elements coming together can form a macromolecule. Now we have a smallest unit known as a monomer, which can combine to form a polymer. So polymers are macromolecules, and polymers are derived from monomers. Examples of biological molecules that we find in living systems are carbohydrates. We have proteins, fats and oil, water, DNA, RNA. In carbohydrate, we are going to have elements like carbon, we'll have elements like hydrogen, and then we'll have oxygen. Alright? In protein, we will have carbon, we will have hydrogen, we have oxygen, we have nitrogen as basic elements that are found in proteins. But a protein may have more than these. For example, you could have sulfur, you could have phosphorus. So, sulfur and phosphorus will come into the structure of a protein molecule depending on which amino acids are actually forming this molecule. So each amino acid that forms a protein or that forms part of the protein has a combination of sulfur, phosphorus as the case may be. Okay, in fats and oil we have carbon. Fats and oil we have carbon, hydrogen and oxygen in fats and oil. And of course our water we have hydrogen and oxygen. Well, I'm showing the simplest elements. I'm not showing any molecular or empirical formula of these substances. I'm just showing the elements that make up the molecules, alright? What will be the monomer of carbohydrate? Which means what is going to be the smallest structural molecule that will make up carbohydrate. So the monomer for carbohydrate will be glucose. The monomer for carbohydrate is glucose. The monomer for protein is amino acid. The monomer for fat and oil is going to be the monomer for fat and oil is going to be fatty acid and glycerol. Fatty acid and glycerol. And then, of course, water is in a very simple form. So when we talk of monomers, these are the monomers. These are the molecules, the smallest units that will combine, all right, to give you these ones. So several units of these will combine to give you these ones, all right. So having shown you what biological molecules are, what monomers and polymers are, the elements that make up biological molecules, and the smallest units in those polymers, I would like us to do a simple demonstration. How can we determine the presence of these molecules? How can we know that a given food substance contains carbohydrate, contains protein, and contains fat? So in today's class, we are just going to go ahead and test for the presence of protein and fat and oil in a given food substance. We have a chemical balance which we'll be using to measure the chemicals we'll be using in our test. All right. We have methanol, which we'll be using to test for fat and oil pellets. We have the copper sulfate. We have our egg here, which is a source of protein. Then we have vegetable oil, which is a source of fat and oil. We have some pickers. All right. So these are the things we'll be using. We use this measuring cylinder in taking the amount of water. Now, we have to test. As I said earlier, we'll be testing for the presence of protein in a food substance, and we'll be testing for the presence of fat and oil. So we'll go one after the other. Now, in testing for the presence of protein in our food substance, we would be using a reagent known as burette reagent. We'll be using a reagent known as burette reagent. Now, conventionally, you don't get the burette reagent in the market, so you have to make it by yourself. You have to make the burette reagent by yourself. That's why we are having sodium hydroxide and copper sulfate. So we'll be using both of these to make our burette reagent, and then we use it in testing for the presence of protein. Okay? So we'll be taking measurements now. So we place a piece of paper on our balance, and as you can see, this without the piece of paper, you can see how the balance is. All right? It's at 0. All right? When there's nothing on the balance, it's at 0. You can see the 0 here when there's nothing on the balance. Now, as I place this piece of paper, you see that the weight of this piece of paper has made the pointer here to go up above the 0, telling you that there's a kind of mass on the balance. So we are going to make sure that we adjust the balance so that we have 0. That way, whatever we put on the paper will actually be getting the mass of whatever we put on the paper and not the mass of the paper. So we'll be adjusting the weight on this. We usually begin with the heaviest weight, and the heaviest is in the middle. So we move this one. I think that the pointer is now at 0, which means we have adjusted the mass of this paper. So this paper is not having weight again, which means whatever we put on the paper is the mass of what we have. So we begin with the sodium hydroxide chemicals. So we get this spatula, we use it to take some amount of this. Is there any change in the reading? No change yet. So we add until we can have a change. Is there a change? Yes, there's a change. So we adjust the pointer so that we can know what's the value of what we already have on the scale. We adjust it to 3.5. Okay, so that's 3.5. All right, so 3.5 minus 3 is going to give us 0.5. So we have sodium hydroxide pellets to be 0.5 grams. All right, so to this 0.5 grams, we are going to add 50 ml. This is the measuring cylinder. All right, measuring cylinder. This is the 100 ml. So we take this and then we put 50 ml. 50 ml is the first line at the bottom. Right. So we have 50 ml of water added to 0.5 grams of sodium hydroxide. So we'll leave this to dissolve and then we get back to it. Now while we are waiting for that to dissolve, we also measure an equal amount of copper sulfate. We also measure an equal amount of copper sulfate. So again, we take our paper and then we adjust this back to 3 grams. And then so this is copper sulfate, is usually blue in color. So we put this and we can see there's a change from the pointer. We move this to 0.5 and then we see if the pointer is at the 0 mark. Yes, we have it at the 0 mark. So we take this and put back in the second beaker. We have to do this carefully so that we don't lose some quantity. Alright, and then we also add 50 ml of water. 50 ml of water is added to this. And then we can use this glass stirrer to stir it together. Okay, so here is our copper sulfate solution. The next preparation we have to make is our egg. Now you get your egg. What we need from the egg is the albumin. So you make sure that you carefully pour out the white part of the egg and make sure the yolk doesn't get in. The reason why we don't need the yolk part of the egg is that the yolk contains most other nutrients, but the albumin contains mostly the protein. The albumin contains mostly the protein. So that's why we have to be sure that what we have is the egg white. So you can see this is the egg white. Nothing of the yolk is in it. But this is rather too much for our experiment. So we'll just pour some quantity out. Alright, so we are going to make a solution out of this. So we add a little amount of water. And then we can use glass stirrer to stir it up. Mix it up together. Okay. So, and then we transfer this into, a test tube. Now we've labeled this test tube A, containing the protein, the egg white. So you can see the color is kind of colorless. Okay, so we'll see what will happen when we add the solutions to it. Right, now we'll take a look at our solution. Sodium hydroxide is ready and copper sulfate is ready. Now it's time for us to apply these solutions to the egg white. So we use our pipette and then we take 2 ml of sodium hydroxide. So that's about 2 ml. We add it to our protein and then we shake it up. I believe you can see what has happened. A chemical reaction has already happened. The cloudy nature of the egg white has been cleared and the egg white is looking purer. Okay, that's one observation, but that's not quite what we are looking for. Take 2 ml of this, and we also add to our protein. Now we can see that there is a visible color change. There's a visible color change. And my friends, this is purple. This is purple. And this is a positive confirmation that this food substance is protein. Because the theory has it that a butyrate reagent added to protein food molecule should be able to change it to purple. So what we have here is classic demonstration of the presence of protein in this food substance. How can we be sure that it is the protein in this that made it to change color? Okay? Now what we can do is that we can get another beaker, and in this other beaker we just add water, which is not containing protein, and then we add our reagents to the water. This is ordinary water now. Alright, this is ordinary water, looking colorless like the protein. Alright, but how do we know that this is not protein? So we also take some amount of this. We also take 2 ml of sodium hydroxide. We add it to this test tube. And then we take 2 ml of copper sulfate, and we add to this. Now you can see that there's no color change. There's no color change. Alright? Which means that it is the presence of protein in this one that made it to change color. It is the presence of protein in this one that made it to change color. This one doesn't change color. Alright? So that's why it is very obvious that there must be something in this one, and that thing is protein. So now we are done testing for the presence of protein in our biological molecule, protein. Now we have a second biological molecule which we label B. This biological molecule is vegetable oil, and what it contains is fats and oil, or this represents fats and oil. Alright, so we will do an emulsion test for this. The test for this is called an emulsion test, and it's very simple. All we need to do is to get some amount of alcohol and then add to this, and then we shake it up together and see if it will change color. Now, we expect it to change color to milky. This color you're seeing here is supposed to change to milky if this is truly containing oil. Alright? So we'll just take some amount of the alcohol we have and add to it. Add 2 ml of alcohol to this. Alright? And then all I have to do is to shake it up. Shake it up sufficient. Okay, so this is milky, obviously. This is milky, obviously. Alright? So this goes to show you that what you have here is fat.